Today is day 21 of learning computational astrophysics, and I continued with regression. Yesterday I started looking at how we can fit a relationship to noisy data, and how making the model more flexible can make it start fitting the noise itself. So how do we actually stop that from happening? Well, one answer is regularization. Instead of only rewarding a model for fitting the data well, we can also penalize it for relying on coefficients that are too large. Ridge regression takes the same least squares lost method as we had before, but adds a penalty that is proportional to the coefficient squared. This deliberately introduces a little bit of bias, but that's so we can reduce the model's variance. This means it is less sensitive to small changes in the training data and can on average make better predictions on unseen data. Lasso regression almost does the exact same thing. Instead of squaring the coefficients, it penalizes their absolute value. We can actually write both methods as the same general constraint to the power of q. For ridge, q equals 2, and for lasso, q equals 1. So basically, they're different versions of the same regularization method. And if we want to talk about this in Bayesian terms, they correspond to different priors on the coefficients. But changing the value of q also changes the geometry, so if we just plot two coefficients, the ridge constraint forms a circle and the lasso constraint forms a diamond. The least squares error forms contours around the best unregularized solution. And what regularization does, it forces us to pick the smallest error point that still lies within the constraint. For ridge, the circular boundary is smooth, so the coefficients are usually just shrunk towards 0. But lasso has sharp corners on the axes, meaning the best solution is more likely to land there. If the coefficient isn't helping the model enough to justify its penalty, lasso can make this effectively equal to 0, removing that feature, and that's why lasso can be used for feature selection. Elastic net regression then combines the ridge and lasso constraints, and is especially useful when several features are strongly correlated. Finally, I looked at Gaussian process regression, which takes a completely different approach. I'm not exactly sure if I understood it too well, but this is what I got from it. Instead of choosing one equation and fitting its coefficients, we start with loads of different curves that could explain the data. A Gaussian process assigns probabilities to all of these possible functions, and a kernel dictates how all of these functions behave, such as their smoothness and how strongly nearby points influence each other. As we add data, the functions that agree with our observations become more likely, and the ones that don't are kind of disregarded. So instead of just one best fit curve, we have a range of curves, and that range tells us the uncertainty in our prediction. But that was quite a bit of theory, and I'm about to just move on to code. So that was day 21. See you next time.